In the last few videos, we've been developing the tools that we need to analyze these circuits that are being driven by sinusoidal sources. Specifically, we've developed the mathematical construct or the mathematical tool of a phasor. We've introduced the concepts of impedance, and now we're ready to move on and show how Kirchhoffs and Ohm's laws can be used in terms of phasors and impedances to analyze these types of circuits. My name is Lee Brinton. I'm an electrical engineering instructor at Salt Lake Community College. Specifically, we're going to derive or demonstrate how Kirchhoffs voltage and current laws apply in these circuits that are being driven by sinusoidal sources, and we'll be analyzing it in this phasor domain. And then we'll give an example of how these laws, these tools that we've developed up to this point, are used to analyze circuits. First of all, Kirchhoffs voltage law. We have here a circuit defined involving three different devices with a voltage reference here plus to minus V1 of t, plus to minus V2 of t, and plus to minus V3 of t. We know from Kirchhoffs voltage law that the sum of the voltage drops around that loop must equal 0, or V1 of t plus V2 of t plus V3 of t must all add to be 0. Now, if we assume that we're operating in the sinusoidal steady state, and we've asserted that in that type of a circuit, all of the voltages and currents associated with that circuit will be oscillating at the same frequency. And let's just say that the source is oscillating at some omega radians per second. That means that V1, V2, and V3 will also be oscillating at that same frequency, but they'll have different amplitudes and different phases. Or more specifically then, let's say that V1 of t will be, let's write it as V sub m1 cosine of omega t plus theta 1. So the amplitude of V1 is V sub m1, and it has a phase of theta 1. Then plus V sub m2 cosine omega t, it's the same omega t plus theta 2, plus finally V sub m3 cosine omega t plus theta sub 3. And the sum of those three terms has to equal 0. Now, let's represent these in terms of phasors. And by that we mean then that the real part of, or that this V sub m cosine of omega t plus theta 1 can be thought of as the real part of V sub m1 e to the j theta 1 e to the j omega t, plus the second term here can be thought of as being the real part of V sub m2 e to the j theta 2, that's a j, theta 2 e to the j omega t, plus plus the real part of V sub m3 e to the j theta 3 e to the j omega t must equal 0. Now, realizing that we're talking about the real part of all of these and that this e to the j omega t is common to all of them, we can rewrite this then as the real part of, and also pointing out that that term right there is just phasor V1, and this right here is phasor V2, and then of course right there is phasor V3. We can now rewrite this as the real part of phasor V1 plus phasor V2 plus phasor V3 e to the j omega t, and that must equal 0. Well, we know that e to the j omega t doesn't equal 0, therefore the sum of phasors V1, V2, and V3 must equal 0, or specifically phasor V1 plus phasor V2 plus phasor V3 must equal 0. This is incredibly important. What that's saying is that up here we have this circuit operating in the time domain. We know that the sum of those three voltages has to equal 0. What this demonstrates is that not only must the sum of the time signals around that closed loop equal 0, but the sum of the phasor representations of each of these voltages must also equal 0. In other words, and this is the final thing, Kirchhoffs voltage laws apply, or law, single law, the Kirchhoffs voltage law applies in this phasor domain in exactly the same way that it does in the time domain. Now, let's take a look at Kirchhoffs current law. We have a similar set of circumstances here where the sum of the currents, I1 of t plus I2 of t plus I3 of t must equal 0. I'm not going to take the time right now to do it. Suffice it to say that the same type of analysis that we just did for Kirchhoffs voltage law results in the sum of the currents, the phasor currents associated with a node must also equal 0. So once again, in terms of impedances and phasors, the sum of the phasors, or the sum of the currents represented in their phasor form, must equal 0 also.